Okay, before I move on to show you guys how to use percent composition to figure out empirical formula or molecular formula, or how to use percent composition in a combustion problem, I just wanted to show you a different way of figuring out the problem that we ended lecture 2 with. So if you don't remember lecture 2, go back to that, and towards the end, I gave you this problem. I said, how many grams of carbon are in 61.8 grams of sucrose? And what I showed you in that video was you get the percent carbon in sucrose, the technique that we learned in the last video, and then you use that percent, you multiply it by the grams of sucrose to figure out grams of carbon. Another way of doing this exact same problem is to use basically dimensional analysis and molar mass and a conversion factor called composition ratio. So it's the exact same problem. We're going to get the exact same answer, but this is just a different way of approaching it. So we're starting off with our 61.8 grams of sucrose, and then we're going to convert grams of sucrose to moles of sucrose. So the molar mass of sucrose, just like we found in the previous video, 342 grams per mole. You put it on the bottom so that you can cancel grams of sucrose, and now you have 1 mole of sucrose. I should write the full thing here, C12H22O11. Sometimes we get lazy and we don't want to write everything, but honestly, you will avoid problems and you will avoid getting confused if you're constantly writing every single unit, every single substance that you're working with. So we have 1 mole of sucrose. So this is the composition ratio I wanted to tell you about. For every 1 mole of sucrose, how many moles of carbon do we have? We have 12. So we write here, for every 1 mole of sucrose, we have 12 moles of carbon. It's the same thing as saying for every 1 molecule of sucrose, we have 12 atoms of carbon. So we can say for every 1 mole of sucrose molecules, we have 12 moles of carbon atoms, okay? So we're going to cancel out moles of sucrose, and now we have moles of carbon, and then we just need one more conversion factor. We say for every 1 mole of carbon, this is 12 grams of carbon. So it is using molar mass and composition ratio to get the exact same number that we got using percent composition in the last video. Okay, so now we'll get into the topic on the what you need to know list of how to find the empirical formula if you are given percent composition. And this is just to remind you, what is the empirical formula? That is the formula of with the lowest ratio of elements in a compound. Molecular formula, the empirical formula is multiplied by a multiplication factor to end up with the molecular formula. So for example, glucose, C6H12O6, this is glucose. This is considered a molecular formula. The empirical formula would be the lowest ratios. So if you divide everything by 6, you end up with CH2O. This is an example of the empirical formula. This is the molecular formula. What would the multiplication factor be to convert this to this? 6. So we're going to learn how to figure out that multiplication factor. But first we want to figure out how to calculate. So calculate empirical formula. If I can spell correctly. Obviously I can't. So calculate empirical formula given percent composition. Okay? So what do? Number one, if you are given percent, you assume 100 gram sample. Number two, convert grams of each element to moles. How do we convert grams to moles? Obviously, you're going to use molar mass. Okay. Number three, divide all the moles by the lowest number of moles. Okay, so those are the basic steps. Let's see, here we go. And let's apply them to this problem. All right, so problem tells you, I have a bunch of different ones, but I'll choose probably 2 to do for you guys. So the problem says that a compound contains 24.74% potassium. Okay, it contains 34.76% manganese, and it contains 40. It's a lot of sig figs. 40.50% oxygen. All right, so we want to figure out the empirical formula based on this information. So the first step that I just told you about is just assume 100-gram sample. So if you have 100 grams, that means you've got 24.74 grams of potassium. You have 34.76 grams of manganese, and you have 40.50 grams of oxygen. Okay, the second step was to convert all your grams to moles. So we need to look up the molar mass of each one of these things. I've got oxygen memorized. I don't have manganese and potassium memorized. Where's my periodic table? Oh my goodness, everything just gets lost around here. Okay, here it is. I found it. Have it always with you. All right. So we're going to start off with our potassium. We're going to say 1 mole of potassium. And we're going to look it up, and it is 39.10. I'm just going to stay with the 4 sig figs since that's what they gave us. 39.10 grams of potassium. All right, and I do the math. 24.74 divided by 39.10. That's 0.6327. So 0.6327 moles of potassium. Erase all this random stuff over here. Okay, now we go with the manganese. Manganese's molar mass is 54.94. So we say 1 mole of manganese is 54.94 grams of manganese. Okay. All right, and we do the math. We have 34.76 divided by 54.94, and that is 0.6327. Also, 0.6327 moles of manganese. Good. Okay, so our last one is the oxygen. That one I have memorized. 1 mole of oxygen is 16.00 grams of oxygen. Okay, we do the math. 40.50 divided by 16, you get 2.531. 2.531 moles of oxygen. All right, so that was step 2. Step 3 says divide by the lowest number of moles. So I have to divide this by 0.6327. I divide this by 0.6327, and I divide this by 0.6327. Why did I choose 0.6327? Because that's the lowest number of moles out of these 3. All right? So when you do this divided by this gives you a 1. And this divided by this, obviously, this gives you a 1 also. What is 2.531 divided by 0.6327? Do the math, and you will get 4. Let me just double check here. See if you get any other weird numbers. So 2.531 divided by 0.6327, and you get 4.000316. Round it. Nearest full number is 4. Excellent. So what is this telling you? It's telling you that the empirical formula has 1 potassium, 1 manganese, and 4 oxygens. So this unknown substance we were working with is potassium permanganate. Okay? So that's how to do these types of problems. Let's do another one, but this time I'm going to make your answer a little bit more complicated. So you'll have to learn what to do when you're stuck with a fraction, okay? You can't leave a fraction in an empirical formula, so we got to get rid of the denominator. Let me show you what we're going to do with that. Let me find one that has that. Yeah, this one works. Okay, so a sample of a compound contains 6.541 grams of cobalt. Now notice, with this one, they haven't given you percent composition, so you just use the grams that they give you. When they give you percent composition, you convert it, you just say, okay, assume 100-gram sample, that's how many grams you have. But here, they didn't give you percent, they just told you, okay, something's got this many grams of cobalt. You write it down. And it also has 2.368 grams of oxygen. All right. So first step is to convert the grams to moles. So let's go ahead and do that. So 6.541 grams of cobalt. We're going to get the molar mass of cobalt. And since we've got 4 sig figs, we'll go with 4 sig figs with the molar mass. It's 58.93. So 58.93. 1 mole of cobalt is 58.93 grams of cobalt. Oopsie, not capital O, lowercase o. Be very, very careful about that. Anytime you have an element that's got 2 letters, the first one is uppercase, the second one must be lowercase. So hopefully you learned that back in chapter 2, but just reminding you, because the way I had put that O, it made it look like it was uppercase. All right, so you do the math. 6.541 divided by 58.93, you get 0.111. I don't know if I could get one more sig fig since we're at it here. Maybe it's 6.541 divided by 58.93, 0.1099. Yeah, it's fine. I'm just going to leave it like this. Okay. And then the next one. The next one is 2.368 grams of oxygen. And I know that 1 mole of oxygen is 16.0 grams of oxygen. I'm going to do the math, or 16.00. I'm going to do the math, and I get 0.148. So 0.148 moles of oxygen. And this is moles of cobalt. Okay, good. We have these two numbers. Which one is the smaller number? The 0.111. So I divide this one by 0.111 and divide this one by 0.111. All right, let's see what we get. Obviously, for the first one, you get 1. Let's see what we get for the second one. So 0.148 divided by 0.111, you end up with 1.33333. You should know what the decimals mean. 0.3333 is a third. 0.6667 is 2/3. 0.25 is a quarter. 0.5 is a half. 0.75 is 3/4. This is all in your book, but it helps if you know these things so that you know what to do when you get into a situation like this. So what is 1.33? That is 1 1/3. 1 1/3 is 4/3. So you have 4/3 for oxygen and 1 for cobalt. Since we can't have a formula like this, can't do that, what you have to do is multiply both of them by the denominator. So multiply this by 3, multiply this by 3. What happens then? You end up getting CO3O4. And that would be the formula, the empirical formula of this compound we were working with. Okay? Good. Next video, we will work with percent composition and finding the molecular formula.